That is a company that is sponsoring this program for you guys. So your school doesn't have to pay anything. How cool is that? So real big shout out to PPG for bringing us this program to you all today. What we're going to do is we're going to take about 30 minutes to explore some liquid nitrogen and some air movement. And you're going to hopefully have a really good time. And it's very thought provoking. So as you go throughout this show, you're going to say, wow, how did that happen? Or why does this work? Write down your questions, because at around 10 o'clock, after 30 minutes, we want to hear those questions. And Sean and myself are going to be really eager to answer those questions. So once again, thanks to PPG. And what I'm going to do is turn it over to the one, the only, the entertaining and educational Sean Carlock.
All right. Good morning and welcome. My name is Sean Carlock, and I am about to show you some of my favorite experiments and demonstrations that we do at the Museum of Discovery. We took all the most awesome things, put them all together, and we call it our awesome science program. The first thing I'm going to show you is the coolest thing you've ever seen in your entire life. I would go so far as to say that I'm about to show you the coolest thing that you will ever see in your entire life. Yes. But that being said, what I'm about to show you is dangerous. So I have to make sure that I protect myself properly. I have these to protect my eyes. I have these to protect my hands. Now, this dangerous thing that I'm about to show you, how would you feel if I told you that right now you're completely surrounded by it? You ever talked about the different states of matter, solids, liquids, and gases? Well, right now, this is a gas. It's in the air around you. But here in just a second, I'm going to show it to you in its liquid form. Now, when you get a gas very cold, it condenses down and changes into a liquid. This is so cold that it's negative 321 degrees Fahrenheit. There's nowhere on Earth that this can exist except for in these very special containers. We call this a dewar. It's like a really powerful, super awesome thermos. It helps to keep our liquid nitrogen cold. Nitrogen gas in the air we breathe in its liquid form, very, very dangerous. And I'll show you why. Now, as I pour this out, you might think that it looks like water. And you would be correct. It does look like water. It's a clear liquid. The only problem is water does not act this way. You might be able to see those bubbles bubbling, and if we get it close up to the top, it kind of jumps out a little bit. Now, you may have seen water act like this. Anytime you put water on a heat source and get it to the point that it's boiling, it'll jump and bubble and look like that. Because that's what our liquid nitrogen is doing right now. It is boiling. Now, how can something that is so cold boil if in order to boil something, you have to get it hot? Well, the air in this room and this beaker that our liquid nitrogen is in is so much warmer than that liquid nitrogen that it causes it to boil. Now, there's a lot of very important scientific things that can be done with liquid nitrogen. They use it in the medical field to cool giant magnets. They use it to burn off warts on your skin. Well, here at the Museum of Discovery, we just like to put things in it and see what happens. Now, speaking of solids, liquids, and gases, is this rubber band a solid, a liquid, or a gas? Well, certainly not a gas. Can't be a liquid because it holds its shape, therefore it must be a solid. But do solids do this? Not normally. This is what we call a polymer. It's a chain of molecules that are attached in such a way that they're allowed to stretch and move and line up. That allows this rubber band to be stretchy and go back to its shape. Now, when we put it into our liquid nitrogen, however, kind of bubbles, you can hear it. See if we can see that on the camera. See how the bubbles get more violent? That's from the heat that's inside of that rubber band. Now, after just a couple of seconds, that rubber band becomes very, very cold to the point that if we tried to take it out of here, whoop, come on, where you at? There you are. If we try to take it out of here and put a little bit of pressure on it, it actually snaps, it breaks into pieces because our rubber band has become brittle. All of those molecules get really close together and they hold on tight to one another. After just a few seconds, it starts to warm back up again and our stretchiness returns. Let's do that one more time. 3, 2, 1. Woo! All the little pieces just go flying. Again, you give it just a few seconds to warm back up. The heat from my fingers helps, and it starts to stretch again. Very cool. Now, I've got another polymer here that is much like our rubber band in that it too is stretchy. The difference between this one and our rubber band is this one you can put something inside. This is a balloon. Now, you could put a liquid inside, you could put a gas inside. Today, I've got a few that I put some gas in. And I twisted them up. Have you ever seen that where people make them into animals? Well, I'd like to introduce you to two of my very good friends. Here they are. Ketchup and Mustard. Now, they do tricks. Yes, they can sit and roll over, all of the standard dog tricks. But these guys are great in aquatics. They like to swim and do tricks in the water. I wanted to show you some of those tricks, but unfortunately, we don't have a swimming pool here today. But we do have this beaker full of liquid nitrogen. Perhaps we should put them inside and see what happens. Now, that balloon is big enough that it really shouldn't fit easily inside of our beaker. But as you can see, it goes right down in. Now, if that one balloon is too big to fit inside of our beaker, it should be quite impossible for us to put two in there at the same time. But as you can see, it just goes right down inside. Now, science is all about observation and hypothesis, educated guesses. So we're going to look at this and we're going to say, okay, one of the few things may have happened. Perhaps our balloons popped and all of the air came out, and that's why they were able to shrink down and shrivel up. But I didn't hear any pop. So I didn't observe any popping sound, right? So maybe somehow the air was able to escape without the balloons popping. That's why we didn't hear it pop. But obviously, the air has to have come out because it shrunk down. There's no air inside. Or perhaps when we talked about what happens to our nitrogen gas when it gets cold, it condenses down and becomes liquid nitrogen. Well, the air inside of those balloons has gotten so cold that it too has condensed down and changed into liquid air, essentially, inside of those balloons. And I can prove to you that that air is still inside, much like with our rubber band. All we have to do is take them out of that cold environment. The warm air in the room starts to warm up that liquid air. It starts to boil. It evaporates. It changes back into a gas. It expands back out and takes up the space that it did before. Look at that. Now, Mustard's been in here for a little bit longer. So I don't know. We'll see how this goes. We're going to take him out and just set him here on the front of the table. Look at that. crackling. It sounds like cooking bacon or something on a skillet. Look at that. That air expands back out. It takes up the space that it occupied before. And there he is, ladies and gentlemen, no worse for wear. Maybe a little frostbite on his nose. A big round of applause for Mustard. Now, generally, this isn't what you would use liquid nitrogen for, but sometimes we like to find other ways of using things. For example, a ball pit ball. They put them in those big pits and you can get in there and climb around. It's lots of fun. But they're not good for much else. They're not heavy, so you can't really play catch with them. They don't bounce very well, so you wouldn't be able to play any bouncing games. But we have found that they are a lot of fun to put inside of liquid nitrogen. And this is going to help us kind of recap all of the things that we have seen so far. Because right now, the outside shell of that ball is getting very cold. The molecules are getting very close together and holding on very tight to one another. Just like with our rubber band, it is becoming brittle. Now, since it's a hollow ball and there's air inside, that air is getting cold. That air is condensing down, becoming a liquid, taking up less space, and creating a vacuum on the inside of our ball. Now, here in a second, I'm going to hit that ball with my tongs. I'm going to break or pierce that outer shell that has become brittle and watch what happens because of that vacuum inside. All right, here we go. 3, 2, 1. It's kind of like it exploded, except it didn't explode, it imploded. It collapsed in on itself as that vacuum went. Look at all the pieces that came off. That's still very cold. That's why I'm wearing my glove to protect my hands. Look at that. Shattered it into little itty bitty teeny tiny pieces. Amazingly cold stuff. Negative 321 degrees Fahrenheit. Now, all of these cool science things that I'm showing you kind of make me hungry. And I haven't had a chance. It's not quite lunchtime yet. So if you wouldn't mind, I'd like to pause for just a second and have a little snack. I brought some Cheetos with me from home. You guys like Cheetos? I like the puffy ones, but I also like the crunchy ones. I've never had the spicy hot ones, but I hear that they are very popular. I'll have to try them sometime. Oh, look at this. Cheetos. Now, it's probably good to note you should not have snacks while you're doing science experiments. If you were talking and not paying attention to what you were doing, if you're at all like me and you talk with your hands, you accidentally drop something, it would end up inside of your liquid nitrogen. And that is not a good place for your snacks. Reason being, that liquid nitrogen is very, very cold. You saw what it did to our balloons. Do you think it would be safe for me to take one of those Cheetos out and put it in my mouth? Whoa. Well, let's find out. That's what I'm going to do. We're going to take one out. I'll give it just a second. Now, that second that I give it allows any of that liquid that's still inside to evaporate and dissipate. So I'm not actually putting liquid nitrogen into my mouth. You would not want to do that. That would be very, very dangerous. So we're going to take one out. Set it down, give it a second. Look at how it makes all my breath look foggy. It's kind of like when you go outside on a really cold day and you can see your breath. It's because the moisture in your breath is condensing into a fog. That's what it would look like on a negative 321 degree day. And you could see how far that fog would roll out. And it even goes farther, but it starts to warm back up again when we don't see that. But I want to give you a little demonstration of why we all are wearing these masks right now. I know they're not very comfortable. They can be a little itchy. But watch this. You can still see when my nose isn't covered how far that comes out. Now I'm going to do one more and make sure that I have my mask on properly. And you'll be able to see what this does. You can see it kept it all right here in my space. So there's less chance of me breathing out and getting poor Thomas with all of my particles that I'm exhaling when I talk. Wow, that is a cold but very refreshing Cheeto. I've got one more thing that I want to show you with my liquid nitrogen, but I'm not going to yet. I'm going to save it for the grand finale. So I'm going to take my liquid nitrogen and put it back inside my doer. The reason for that is if I left it inside of this beaker, by the time we were ready for it, it will have been completely evaporated. You can see this was full when we started. Look how far down that has gotten just from evaporation as it turns back into nitrogen gas. You can see all the snow here on the sides of the beaker from the moisture in the air condensing on the outside of it. All right. Because now we're going to talk a little bit more about that air movement that we saw when I was breathing and you could see my breath from that Cheeto that was really cold. And talk about a certain way that air moves, a little something called a vortex. That sounds like some kind of super awesome space alien pirate or something. Vortex the Destroyer. Yeah. Well, could any of you tell me what is a vortex? Kind of a tough question, unless, of course, you have studied vortexes. So let me ask a simpler question. Have any of you ever taken a bath? Good. When you get done taking a bath and you pull the plug and the liquid goes down the drain, does it just go straight down? Or does it do something as it goes? It spins, doesn't it? That spinning or rotation of that fluid is a vortex. Now, it can happen in air, it can happen in liquid. In your bathtub, of course, that's water, so that's a liquid, isn't it? And I can show you what that looks like using this cool vortex generator that we've built. Now, you can make one of these with a couple of soda bottles, some way of connecting them here in the center. Now, if I wanted to get this liquid from that bottle into the one up there, well, science says turn it over. Gravity's going to help. It's going to pull that liquid down. But that's not working very well, is it? You see, as the liquid tries to go down, the air inside of this bottle tries to go up, and they run into each other in the middle. So in order to allow them to more efficiently trade places, that's where our rotation comes in. Just give it a little spin to get it started and watch. Now we have a vortex. Usually people see this and they go, oh, it's a tornado. It's exactly what it looks like. Now in the water, we would call that a whirlpool. And right down the center of that whirlpool is a column of air that acts almost like a straw or a tunnel that allows the air to come right up through the middle while the liquid spins around and goes down the outside edges. That way they don't run into each other. They're able to trade places a lot more efficiently. Pretty cool. So that is what it looks like in liquid. Here in a moment, I'll show you what it looks like in the air. But there's another medium that we can use to create a vortex, a little something known as plasma. Now, some of you maybe have heard it called that. Others will know it better as fire. That's right. We are going to make a fire tornado right here in our laboratory. In order to do this, we need a few things. This is our trash can of science. Yes, on a little lazy Susan here. That is what gives us our rotation. Remember, in order to have a vortex, it has to be rotating. All right. In order to have fire, we need a couple of things. One being oxygen. And as Thomas and I are both still standing and walking around breathing, we know that there is sufficient oxygen in this room. The next thing we need is a fuel, something to burn. We're going to use a little bit of isopropyl alcohol. We'll put this right down inside of our trash can. And the last thing that we're going to need is a heat source or a spark, something to ignite our fuel. And I'm going to use this. All right. Make sure we don't have anything close by that might combust. Safety first in all things that we do here at the Museum of Discovery. Look at that. We have successfully created fire. But it doesn't look like a tornado, does it? Because we still need the rotation. Look at that. See how it grows and gets taller? Fire tornado. What if we go the other direction? Do you think it'll work? This is what they look like in Australia. Wow. Now, I joke about things, going the other direction in Australia, but it ties in with our fire tornado because this isn't something that you're normally going to see here in the US. Maybe during the wildfires and things that they have, if the wind is just right, it will whip up a little fire tornado. But I have heard stories of this happening more frequently down in Australia. Can you imagine walking out of your house one day and that's what you saw as you were walking down the street? As if a tornado is not frightening enough, if it was a tornado of fire, can't imagine. Now, air movement. Vortexes help air to move more efficiently. And we're going to do a little demonstration using my super cool, awesome cups of science to show you how air can move more effectively with a vortex. If you'll join me right over here. All right. Do you think if I took a big, deep breath, that I would be able to blow over those cups with just my air? Seems like maybe. Let's give it a try. Interesting. Now, remember when you saw the Cheeto making that air come out, the way it was all over the place. It was very turbulent. It's difficult for us to focus our air in a small enough, tight enough area that it would have enough force to blow those over. That is why I brought this. Now, to the untrained eye, this is a trash can. But to the highly trained scientific eye, this is a trash can. That's what it is. You can't change that fact. But it's no ordinary trash can. It has been modified into a bona fide vortex cannon. We cut a hole in the bottom right here and put a rubber sheet on the top right here so you can play it like a drum. What happens is when you hit that drum head, it forces the air inside to come out through this hole right here. Now, thanks to a gentleman by the name of Bernoulli, we know that any moving air or fluid creates low pressure. Basically saying it's going somewhere it can't push out against the things around it. So as this air is moving out, the higher pressure air around it swoops in to fill that space. As it does, it meets that column of air and it starts to do this. And then you get rotation. And anytime we have rotating air, we have a vortex. Allows us to do cool things like this. Ooh. Haha, pretty cool, huh? Problem being, what does our vortex look like? We don't know because we can't see the air. If you move your hands like this, you can feel the air. We breathe it. We know that it's there. We can see it when it moves other things, but we can't see the air itself. So if we wanted to see what our vortex looked like, we'd have to add something to it. And that is why I brought this. A little bit of artificial fog. That allows us to see the air as it moves through it. All righty, here we go. What does our vortex look like now? Some people say it looks like a circle or a halo. My personal favorite, people think it looks like a donut. Look at that. Now, we did say that in the air, a tornado is a vortex. Does that look like a tornado? It really doesn't, does it? Oh, look at this little one. Just kind of taking his time. Little baby vortex. Oh. Now, if you could take a tornado and grab it by the ends and twist them around and stick them together, this is exactly what it would look like. The whole outside of these little circle halo donuts is spinning, it's rotating. These are all vortexes. Look how it just propels itself forward. Look at that. Chasing them down. Wow. I could do this all day long, but I'm pretty sure that if I did, we'd probably set off the smoke alarms. So I should probably stop. Vortexes, spinning liquid or gases, a much more efficient way for air and fluids to exchange places and move around. Now, I told you that I was going to save one last thing with my liquid nitrogen for you for our finale, and I always keep my word. Now, to do this, we've got to have just the right amount of liquid nitrogen. So we've got these lines on our beaker here, so I'll be able to see just how much we need. Our snow is all melted off. Protect my eyes and protect my hands from our extremely cold negative 321 degree Fahrenheit liquid nitrogen. Kind of hard to tell with it all jumping around like that, but I think that's just about right. So we're going to take that, and then we're going to add to it some boiling hot water, 212 degrees Fahrenheit. Negative 321, 212. That's a difference of over 500 degrees. If we combined those two in this middle or in this glass beaker, it would explode. So what we're going to do is I'm going to put the liquid nitrogen inside of this metal container here, inside of this metal pitcher. Whoosh. Look at all the air condensing around it. It's so cold. Now, the other thing we're going to need for this is our boiling hot water. It's time for tea. I'm going to pour some of this in here. Now, this also looks like it has some kind of fog coming off of it, but we know that that is steam, right? Because our water is really, really hot. Now, we're going to take these. We'll do a countdown from 5. We're going to combine them rapidly and see what happens. This is my favorite part. Here we go. In 5, 4, 3, 2, 1. Look at that. Did you see that? All of that gas and fog coming up out of the top of that. Wow. So the second that our hot water hit that liquid nitrogen, it causes it all to instantly evaporate. Now, remember how we said that a liquid takes up less space than a gas, like inside of our balloons, right? So all of that liquid that was in here turned into a gas, and it wanted to take up a lot more space. That's why you saw it come shooting out of the top. Look at that. So all that's left inside is very, very cold air. You can see how it comes out and it's going down, isn't it? Our steam on our cup went up, right? But this is very cold, so it sinks, it goes down. If you put your hand underneath it, you can feel just how cold that is. Sometimes we even end up with a little bit of ice in the bottom. A little bit on the sides, but I don't know if you'll be able to see that. Instant ice. Isn't that amazing? That's just how cold this liquid nitrogen is. I hope you enjoyed that. I know I did. It's my favorite part. Thank you so very much for joining us today. Like Thomas said, we do have some time to answer any questions that you guys might have. So I don't know if we want to have people go ahead and I can see you here on our monitor. If you want to turn your cameras on, if you have a question, just raise your hand and Mr. Thomas will call on you. If we have a question from the classroom, if you guys want to just have a representative raise their hand so we can see you in the camera, and then we will call on you. You can ask your question, and we will do our best to answer it. There he is, the man behind the camera, getting all those amazing close-up shots. Give Mr. Thomas a big round of applause. Making sure you guys get to see all the cool stuff.
The true round of applause goes to Sean. What a great show. That was awesome. So we are really eager to hear your different questions. So let's, I'm going to pull this into a gallery view so I kind of see everybody. Looks like we got someone lined up at the laptop in the classroom for our first question. Let's unmute and hear it.
Well, I've been hearing about this thing called dry ice cream. Is it good for lactose people like me?
That's a good question. I'll take that one for you. So if you're creating an ice cream with say like dry ice or liquid nitrogen, one thing to keep in mind is that the ingredients that are used within the flavorful side of things, that's still going to affect you just like any other ice cream. So if you use like milk or cream, whether it's liquid nitrogen ice cream, dry ice cream, snow ice cream, or whatever, if it has those products in it like milk and cream, that is going to upset your stomach. The liquid nitrogen and the dry ice, that is used to make it colder. So that's just used to lower the temperature of it, but the ingredients will still affect you the same way with the milk and the cream. That's a good question. Thanks for asking it.
Very good question.
What is our next question this morning?
Okay, so I got a question. How did you get the texture of the van if it was so cold?
Ooh, good question. I'll let Sean take that one.
Very good question. So when you bring it out, it's so much warmer in this room that it heats up pretty quick. But again, I wouldn't want to grab it and just hold on to it. You notice how when I pull it out, I squeeze it real quick, the pieces fly away. So I'm not just putting it on my skin and keeping it there. If I did, that would probably be pretty painful because that is a very cold rubber band when it first comes out of there. But because of the temperature in the room, the fact that I'm not just grabbing onto it and holding it firmly with my hand, are a couple of the things that help to protect me from that cold. But that's a very good question.
I got
Thanks for that
another
one. Let's
question
get
too.
our. Oh, got a second one. Let's hear it.
I
Perfect.
got another was some of that magic?
Absolutely yes. Because what is magic? Magic is really just sciences we don't understand, I would say. And a lot of magic is based off of scientific principles. So, yes, it was magic and it was also science.
Okay, thank you.
It was certainly magical, I will say.
Can you use melted metal and then put some water in it and then it will do the same thing? Like can melted iron or metal can if you put some water in melted iron, can it do the same thing? Like explode?
What you would see is rapid evaporation of that water. So that would be steam. That would be very hot steam coming up as that water was hitting that hot metal and it was evaporating very quickly. So yeah, you would get that same kind of all of that steam coming up. But it would definitely be a lot hotter, whereas this is